All right, so one of the questions was, if you go back to where you guys traced this lemon, you traced it in the first quadrant and then rotated it. How can you find the radius of the lemon? If we're saying where you traced it is f of x, what would be the radius? The height, the value of that function at each x value. So it's basically f of x. So in this chart, we could call the radius f of x. And then the height of each slice was the change in x, or like if you're looking at it that way, it's kind of looks like the width. So that's going to be delta x. So then when you find the volume, it is pi, and then r squared would be f of x squared. And then change in x, delta x translates, hold on. That would be times the change in x. And if we took that to an integral, you're going to find the integral from one value to another of pi f of x squared, and then delta x translates to dx. All right. And then how could you make your measurements more accurate? What did y'all say for the last question? If you're just slicing it. Did y'all not say anything?
We could make more slices.
More slices. More thinner slices. But if we do an integral, you're basically doing an infinite number of slices. So the integral will actually give you the volume. I have to do this really fast. All right. So we're going to use the disk method to find the volume of a rotated solid. So some solids are generated by revolving two-dimensional regions, so 2D regions, around an axis of revolution. Let's just say of instead of or. If the axis of revolution is a boundary, so it is actual touches the area you're revolving, then each slice is a circular disc, like a slice of a lemon. Sorry. Okay, so I'm going to try and draw the situation on your notes. It's probably not going to be beautiful. If we took that right there and we revolved it around the x-axis, it kind of looked like a vase, I guess. Or a top. And if we wanted to find the volume, it's going to be the integral from a to b of pi r squared dx. Now, because pi is a constant, we're going to pull it out in front of the integral. And then sometimes you're revolving it around a vertical axis, like the y-axis. And so it's the same thing, except your upper and lower limits, you're going from bottom to top. So they're going to be y values, and it's going to be r squared dy. So r would have to be in terms of y. All right, so what we really need to be able to do is to find the radius. And I'm going to talk to you today about finding the radius in a way that you don't really need today, but you do need tomorrow, but it will work for today also. So what you're going to do is draw a line from the axis of revolution to the curve, and then r is either going to be the top minus the bottom, or it's going to be the right minus the left. So similar to what we were using when we were finding the area between two regions. All right. So on example 1, We have R is the region bounded by y equals x squared, the x-axis, and the vertical lines x equals 0 and y equals 4. So let's just draw that real quick. So the square root of x is this graph right there. So it's bound by the x-axis, which we already have. The vertical line, x equals 0, which is the y-axis, and the vertical line, x equals 4, which is there. So here is our region. Whoa. Kind of went outside of it a little bit. And we're going to revolve it around the x-axis. So what we really need is the radius. Right? And then to find the radius, we're going to draw a line from the axis of revolution to the curve. So right here. All right. Our curve is y equals the square root of x. All right. So with this type of revolution, we're going to do the top minus the bottom. So the top here is the square root of x. That's what y is at the top. What is y at the bottom? 0. So in this case, it's not really necessary, but I'm getting you ready for what we have to do next. All right, so we have what we need to find the volume. We're going to do pi times the integral. Right? And then if our function or our radius is in terms of x, we're going to go from x to x. So from left to right, which is going to be from 0 to 4 of the radius squared dx. All right. So we are going to square the radius and just get x. All right, and then we're ready to integrate. So we have x, so we're going to add 1 to the power and divide by our new power. And then we're going to plug in 0 and 4. So v is going to be 8 pi. Now they don't all turn out so pretty, so don't get too frustrated. I'm fine when you guys do your assignment as you leave it really, really messy. So if you have a bunch of fractions to add, just don't add them. Just leave it written out as like 5 plus 1/2 plus 7/8 or whatever. That's fine. Okay, let's do another one real quick. So we have the same function, y equals the square root of x, but it's a very different region. Okay, so this time is bounded by that same graph, y equals 0, which is the y-axis, and y equals 5, which is a horizontal line here. So it's kind of hard for me to shade, but that's kind of it. And we're going to rotate it around the y-axis, so it's going to kind of look like a funnel. Okay, so again, when we're finding the radius, what we're going to do is draw a line from the axis of revolution to the curve. So our axis of revolution is the y-axis this time, and we're going to go to the curve. Now, whenever we are doing a vertical revolution, our function needs to be in terms of y. So we're going to take our function and write it in terms of y, or solve it for x. Which in this case is not hard to do. So we have y equals the square root of x. So x should be y squared. All right. So our radius, in this case, is the second situation where we're going to do the right minus the left. So the right is y squared. This time the left is 0.
So it's 3 in terms of
Y. Yes. So when we set up our volume integral, because our function is in terms of y, our upper and lower limits have to be y's. So what are they going to be?
2.
Good. So we take y squared and we square it, and then dy. All right. Don't forget that we need to square that radius before we integrate. It's going to be a mess if you don't. All right, so here we go. We are going to add 1 to the power and divide by our new power. And we're going to plug in 0 and 5. And I know I'm going super fast, but we're running out of time. So 1/5 times 5 to the 5th, and then minus 0. So that's going to be 625 pi. Okay, and then this last one is a calculator question, and it looks like a graph that I've seen on the AP test. Now they'll put some kind of volume on a free response for sure. We're going to learn several different ways to do volume, but they're going to definitely have one on there. All right, so this time we have this region. This bounded by y equals the natural log of x and y equals 5 minus x. It's bounded by the x-axis also. And then this is going to be rotated around the x-axis. So that's our region. Now finding the radius this time is a little different. Because if we draw our radius from the axis of revolution to the curve, there is going to be the natural log of x minus 0. But if I do it here, it's going to be 5 minus x minus 0. So we're going to have 2 different integrals. Now, if we had more time, I would remind you how to find this intersection point. Like we need to know when it's changing over from the natural log of x to 5 minus x. So you would just type each of those in and find the intersection point. And I'm just going to go ahead and tell you, it's 3.69344414. So on the AP test, you would need to say that A equals that. And then every time you need that decimal, then you're just going to put A. You don't have to rewrite that decimal over and over and over again. Okay, so I'm going to kind of separate this like that. And so this first integral, I have the pi. And then I'm going to go from 1 to A of my radius squared dx. And then plus pi. And then what are going to be my lower and upper limits on the second interval? A to 5, good. And it's going to be 5 minus x squared dx. Right. And if it's a calculator question, do not try to find these integrals by hand. You could. It's not that difficult to do square that and find the integral, but if you do it in the calculator, it's fine. I mean, if it's a calculator question, they don't care if you can do it by hand. They want you to be able to type it in. So that would be the volume of that revolution. All right. Do you guys have any questions? All right, your assignment is on the back. And make sure, I wrote a note to tell you guys to be sure to square the integrands before integrating. And you can leave your answers messy, which means don't worry about adding and subtracting fractions. Just leave them messy. And you can see when you check the answer key, I left mine messy too. And then I did say on the very last one that you could use a calculator. I put it on here, but I don't know if it's on your copy. So does this say calculator on yours? Okay. So on number 4, go ahead and write that can be a calculator question if you want to.